we are going to start discussing about general physics 1, or we can say physics 14.1. First topics we are going to discuss today, 1D motion. So in 1D motion, we'll discuss about some plots like position versus time plot, velocity versus time plot, and acceleration versus time plot. And we'll see how plot represent the physical scenario. So we know about when we have some distance, like if we represent our distance with some direction, we can tell it as a vector quantity, and which is displacement. So if a person going towards his home from a point, we can tell this as a displacement. Means if he go suppose a person is standing in a point, he covers some distance like 5 kilometer, 5 mile. He covers some distance by walking, suppose. So this we can mention as a distance. But if the man go like 5 miles towards west, suppose, then this will be displacement. So the basic difference between distance and displacement is one is a scalar quantity, another one is vector quantity. Okay. So now we are going to discuss about the plot. So first we draw position versus time plot. So suppose this is our x-axis, this is y-axis. So if we represent x-axis by using t is time, and the unit we know second. The unit of time is second, and position, like in y-axis, we are marking position, and the unit for position is meter. So we are using x as a position. So and change in position, we will use the symbol del x, change in position. So now we draw a physical scenario, and we'll draw a graph, and we'll discuss how the physical graph is representing physical scenario. So here we can see different types of variation. We can see line like this, we can see line like this, we can see line like this, we can see line like this. We can see different types of line. We can see this line. So we'll discuss which line is representing what. Okay. So let me start with the parallel line first. So okay. So first, this is position 0 meter, suppose 1 meter. So I'm using the SI unit meter, 2 meter. So like this up to 5 meter, suppose. So if I mark the position A in 1 meter and position B in 5 meter, suppose, okay. So here we need to mark this line too, 1, 2, 3, 4, 5 meter. 1, 2, 3, 4, 5 meter. Now, if a car stop in this position, in 1 meter position, like it's a stop, it's not moving, how do we represent this graph? We'll draw a parallel line, like you can see parallel line, horizontal parallel line. So horizontal parallel line means in 0 second, the car was in position A, right? Position A. In 1 second, still the car is not moving. In 2 seconds, not moving. 3 seconds, not moving. 4, 5. So that means the car does not move at all. So then we represent our graph like this, okay? So that means if we see position versus time plot, and if we see this horizontal line, like parallel horizontal line, what we will understand? We will understand there's no velocity or no speed, 0. And if V is 0, A is also 0 in this case. And here you see one thing, our X is not 0, X is 1. Yes, the change in position is 0. Why? Because initial position was like 1 meter and final position 1 meter. That means change in position is 0, but position is not 0 here. Position is 1 meter. So try to understand this. And how do we define velocity? Velocity is, when we talk about velocity, it's final position minus initial position divided by the total time. So sometime we represent like del x. So del x representing final position minus initial position, and t is time. So this time is change in time, means how much time it take. So in this scenario, whatever time we put in below, like 1 second, 2 second, 3 second, but all the all scenario we can see our initial position and final position is the same position. That's why v equal to 0 here. Now if we draw another graph, position versus time graph, like this, x versus time graph. Now if we draw a line starting from 0 and moving straight line, it's a straight, due to my drawing it might be some wave, but it's a straight line. Assume it's a straight line. Okay, so if it is a straight line, what it will represent, like 1 second 1 meter, suppose 2 second, in 2 second it went to 2 meter, in 3 second 3 meter. If we draw something like that, so what does that mean? A car starting from 0 position, in first second it went to 1 meter, in second another meter, third second another meter, fourth second another, like. So here you can see uniform velocity, means in this case our velocity is not equal to 0, but our velocity will be constant here, because we can see this is constant. Okay, so in other words we can say this line as a like non-zero constant velocity. Non-zero, in our case when we discuss 1 meter in 1 second, 1 meter in 1 second, when we are telling, so in that case our velocity will be 1 meter minus 0 meter, 1 second minus 0 second means 1 second. So 1 meter per second. So here our velocity is non-zero, but velocity is constant, 1 meter per second. So 1 meter per second, what does that mean? In each second, it is going 1 meter. So the velocity is not increasing. So velocity is not increasing means our acceleration. What is the definition of acceleration? Definition of acceleration in change in velocity over time. So change in velocity is 0. Why? Because velocity, all the way velocity was 1 meter per second. So in first second it was 1, second it was 1. So 1 minus 1 equal to 0 over t. So that means our acceleration will be 0 in this case. Okay. Now we'll see some other example, position versus time. So here position versus time, if we draw like if it's position and it's time, so this line velocity 0, this line 1. Okay, line 2, if we draw like this line 2, velocity is constant. Now if I draw something like that, the curve like this case our velocity like is not constant, our velocity is changing. So in this case our acceleration not equal to 0, means suppose in 1 second it went to 1 meter, suppose 1 second, in second it went to 3 meter. See, first second 1 meter and second 2 extra. So that means in our velocity in first case 1 meter per second, in second case 2 meter per second, in third case it could be like 6 or 7, suppose 7 meter in third second. It's like this. So in this case it can be 4 meter per second, right? So see, here velocity is changing. When velocity is changing, then we got our like acceleration. So in this case, this is positive velocity. That's why we are using term acceleration. If it is negatively if we draw the curve like this, in 1 second, suppose it go 4 meter. In 2 seconds, it go 5 meters. So like this, if you draw like this, then you can see this velocity is decreasing over time. Then we can tell it as a deceleration. So this is the case for the position versus time graph. Now we are going to discuss about our next graph, velocity versus time graph. So here you can see velocity versus time graph. Velocity, the unit is meter per second, obviously, and time is second. So time second. So in this case, if we draw a horizontal line, if you remember, when you draw horizontal line in our position graph, we tell our position is equal to not equal to 0. So here this means velocity not equal to 0 if this is velocity versus time. Remember, if this is x versus t plot, if we draw like a parallel line to the horizontal axis, then we can say velocity is 0. But in this case, velocity is not 0. Why? Because you can see we are representing this axis as a velocity. So maybe it is 2 meter per second. 2 meter per second. So in 1, 2, 3, 4, 6. If we draw some a straight line like this, what does that represent? It represents the car is moving, car or object is moving with 2 meter per second. So in first second, it went 2 meter. First second, 2 meter. First second, it go 2 meter. Second, like 1s. It's another 2 meter. So altogether in 2 seconds, it 4 meter, right? So like this. So if we draw like 1 more second, it will be 2 meter. So that means the velocity is not 0, velocity is constant. And we know if the velocity is constant, that means velocity is not changing. So there is no acceleration. So acceleration will be 0 in this case. Okay, because we know if we are driving in highway and if we don't change our speed, so there will be no acceleration. We need not to press the acceleration button. If we press the acceleration button, our speed will be changed, right? So another plot, like same velocity versus time graph, if we draw, and if we draw like this here, see, here is change in velocity. Change in velocity means acceleration. We will get some value for acceleration. Del V over del T. Sometimes we denote, like we represent like this. So in this case, if suppose is 1 second, 1 meter per second. In 2 seconds, it's 2 meter per second, 2 meter per second, 2 second, 3 second, 3 meter per second. So you can see it's increasing. In 1 second, it was 1 meter per second. In 2 seconds, it's 2 meter per second. That means increasing, speed is increasing, but speed is increasing uniformly. So now if we want to calculate for 3 seconds, what was the acceleration? So from from here to here, how much it accelerates if we want to find it? So we can say 3 meter per second minus 1 meter per second. So this acceleration happen with like the time duration. What is the time stamp for this? So suppose this is our 1 second, this is 2 seconds, this is 3 seconds, suppose. This is 3, this is 2, this is 1. So see, the time is 3 minus 1 equal to 1. 3 minus 1 equal to 2. So 2 meter per second and 2. So 1 meter per second square. That means each second it is increasing, the velocity is increasing by 1 meter per second. In each second, that we can see 1 plus 1 equal to 2, 2 plus 1 equal to 3. Suppose this is not 3, this is 6. Then this should not be uniform. It should be, the curve should be like this. because that is not uniform increment. Why? Because you can see 6 minus 1 equal to 5, right? 5. And in 2 seconds, 5 means 2.5 meter per second increasing, if this point is 6 meter per second. But in first second, we can see increment was only 1 meter per second. In first second, from 1 to 2, but 2 to 3, we can see 3 increasing. So that is not uniformly increasing. In that case, our acceleration will have some value. So this case, our acceleration will have some value, but in when it was 3, our acceleration was constant acceleration, right? So what we understand from here? We understand from here, if we have a velocity versus time graph plot, velocity versus time plot, if this is a straight line uniformly, that means we have acceleration, but which is constant acceleration. Okay. But if we draw a line like this, that means it's not constant acceleration. If we draw like this, that means velocity is increasing. That means it's deceleration. But we cannot see any graph is going back. Why? Because we cannot go back in time. So all we need to represent. So if we talk about negative velocity, that means we will draw this type of line. Why? Because velocity is decreasing. How velocity could be negative? If the car or the person or object is going opposite direction, then we can tell it as a negative velocity. So here few formulas are important in this 1D motion chapter. So the formula, like equation of motion. So you already know from your previous classes, like from your college physics. So del x is change in distance is v initial into t plus half at square. This is one of the formula. And we have like first formula, we know first formula is v final equal to v initial plus a t. Second formula, we know our del x equal to v final plus v initial over 2 into t. And third formula, we know del x equal to v initial t plus half a t square. And fourth formula, we need to use v final square, v initial square plus twice a del x. So how do we use this formula? This formula we have to use, suppose x, this v initial, this is v final, this is x, suppose x, this is a, and this is t. So in first formula, so if we know, if we have 3 known value, suppose this value is given, this value is given, and this value is given, we need to find other value. So missing term is del x. Suppose del x is missing here, suppose. So if we have 3 unknown value, one value we need to calculate. Which formula we should use? We have to use this formula. Why? Because you can see in this formula, 1 term, 2 term, 3 term, 4 term. This 4th term is present. So in this 4 unknown, if 3 is given, we can find another one. You have to use this formula. But if our del x is present, means we have some value for del x, and we have some value for v initial, v final, we need to calculate the time. Which formula we should use? We should use second formula. Why? Because in second formula, unknown is 1, 2, 3, 4. This v initial, v final, del x t. So how do you know which formula we need to use? By using this chart, we can understand. You need not to use the chart, but it's for your understanding. I'm using this chart because if you understand without chart, that's okay. So you can see, if our v initial given, our acceleration given, del x given, there asks about t. So we need to use this formula. Okay, this formula we need to use. So now for the fourth one, you can see our V final given, V initial given, A del X given, A. So if we are asked to calculate our del X, if these three quantity given, like the car start from 20 meter per second and its final velocity is 60 meter per second, or we can say the car stop like with some acceleration for 2 meter per second square. So how much distance it cover? So in that case, we have to use this formula because there's no mention about time. They are asking for our like how far it goes. Okay. So that's all discussion about 1D motion. Now we are jumping into 2D motion. So like we'll discuss 2D motion, but before we discuss 2D motion, we will discuss 1D motion in incline constant acceleration. Like we discuss, we in our case 1D motion, we did not had any angle, right? We did not discuss about any angle. But what happened if we have a 1D motion, but with some angle? Like if some object is rolling from like a ramp, rolling from a ramp. But what happened, we can see we are going from the ramp, we are, if the car is going down. So what will happen? What will happen when there is inclined like motion in inclined surface? Okay. So we know we are going to discuss about 1D motion inclined constant. 1D motion inclined constant, which is our topic number 02. So for this, first we need to understand the Newton's second law of motion. So which is F equal to ma. So F is representing force, M is mass, and A is acceleration. Okay. So this is very important formula. We need to know because when we discuss about the acceleration, we know it depends on force. So like before I discuss the like inclined surface motion, I want to introduce with you some trigonometric topics. So if we have a force going on some direction, how do we represent this force? Like how we can say suppose one box is lying in the floor. So you are pushing, suppose you are pulling with some rope this direction. How far the box will go? You are using force with some angle, right? With some angle you are using the force. But how do we know how much it shift? Because if we if we use force, if the box is lying there, if we use force 10 Newton, suppose you use 10 Newton, and the mass of this box is suppose 2 kilogram, we can easily say what is the acceleration here. How? F is given 10 Newton and our mass is given 2 kilogram, right? So what will be our A? Simple. If we divide by m both side in this equation, suppose in this equation we divide m both side. So m cancel out, F over m equal to our A. So A equal to F over m. So that means 10 Newton divided by 2 equal to 2 kilogram. So it's like 5 meter per second square. So in this case we can set, but what happened? This is 10 Newton, this direction. How we can represent? Can we do the same math? No. Because when we are using force, like there is some component, like this is dividing into some two component. One component we can define as a vertical component. We represent by using the symbol Fy, vertical component, and this is called horizontal component. And we know from our like earlier trigonometry course, if we have some like going some hypotenuse, going some force in hypotenuse, if we want to find the distance y and x, if it is r, how do we find y, or how do we find x? We know from trigonometry cosine. What is the definition of cosine? Cosine theta equal to adjacent by hypotenuse. Adjacent is our x and hypotenuse is our r. So that means our x equal to r cosine theta. How? We are just multiplying r both side. We are multiplying r both side, right? So r cancel out. So the x equal to r cosine theta. So same, our sine theta equal to opposite divided by hypotenuse y over r. So y equal to r sine theta. So now if we draw our force F, so what will be the horizontal component? F cosine theta, right? Because this is our x. And this portion will be F y equal to F sine theta, right? So this you need to understand. Now, if we are discussing about 1D motion in inclined constant surface, that means we will discuss about only 1D, not the second dimension. So, if we have like some inclined surface, if we draw some inclined surface like this is a ramp. Suppose is a ramp. In that case, we can see like what's if the box is there. So in this point, our G is working, like the G means acceleration. And it is working towards which direction? Our in horizontal, like you can see, this is our distance, and this is if we draw like this, it's moving. It's moving this direction, right? So in this direction, how do we represent our fx? We can represent fx equal to max and fy equal to may. So in this case, we are not lifting. We are this box is not flying, so it does not have any motion. It does not have any motion y direction. So we can just simply say like our ay will be 0 in this case, right? So in this case, our fx will have some value, right? Because it's moving towards the ground, right? So it's just like you need to think some like if you think like this, it will be easier for you to think, right? But if you rotate the axis, means if you draw like this, so you can see this is our x-axis and this is our y-axis, right? So we don't have any, it's not moving upward. That's why ay 0. It's moving only x-axis. So we will have this acceleration, and this acceleration we know is due to gravity, like force due to gravity, like acceleration due to gravity. So it will be mg, right? But if we clearly draw our picture, like if this is our box, if this is our angle, and this is our like ground, right? Ground. So carefully observe. We have to find this line, right? We have to find this portion, right? This portion means parallel to this portion. Because we know if we draw force like this, both are equal, right? Because parallel. So we have to find this portion. So this portion means, suppose this portion is our y. So this is theta, and this is our r. So see, this direction will be sine theta, right? Because you know opposite over hypotenuse, right? So this direction will be mg sine theta. So don't get confused. Because why? Because in our like previous discussion, when we discussed about the component, sine theta was the vertical component, right? But here we are using sine theta for our fx because it's inclined. So in inclined, the g is making angle with this. So even we are using this direction, it will be mg sine theta. Okay. So what we understand, fx equal to mg sine theta, that we find. And another thing we know, f equal to ma, right? ma. So if it is fx equal to max, so we can write max equal to mg sine theta, right? So we can divide m both side, cancel out. Our ax equal to g sine theta. So now if we find some angle and if we know our like our g 9.8, we can find acceleration, right, by using this formula. So now we'll use another formula. So you can see this we know del x equal to our v initial plus half v initial t half at square, right? This we know from our formula, like equation of motion formula. So del x we can write it x in final minus x initial equal to v initial t, this is t, okay, plus half a t square. So when you using x, that means it's initial x axis, this v initial x and ax, right? So we can write down ax equal to our our initial xf x initial. We can write down in that case when we don't have we have some del x or x distance, right? So suppose we get some some inclined surface from here, it's going here to down, it's going down. So there will be some distance. If this is x, then we can say x equal to, initially we don't have any velocity, so this will be 0. So we can write x equal to half ax t square, right? Because this is 0 and this distance is x. So we can write ax equal to 2 into x. We multiply 2 both side, 2x and divided by t square. So t square. So here you can see we find our ax equal to 2x over t. Now in previous page, we already got our ax equal to, if you remember, g sine theta. If you remember g sine theta, right? So here we got ax equal to our g sine theta. See, g sine theta. So in this case, we can write our g equal to ax. If we use the formula ax, estimate. So we can use ax equal to twice x over t square. And we can write another formula 2x over t square, right? This one, going to explain a little bit or you will not understand. So what we write in our previous line, our ax equal to 2x over t and ax equal to g sine theta. Now in that case, if we have a ramp like this, if we have a ramp like this, so if we are drawing like this, sine theta means sine theta, if we draw this sine theta, you can see we will have some displacement. This theta and this theta will be same. So if this theta and this theta is same, so we will have some height, right? And we will have some length. We'll have some length and height. So what is length and height? So if we rewrite this equation, g sine theta equal to ax, right? So next line we got g equal to ax over sine theta, right? We just divide sine theta both side and we plug the value of ax. So that means 2x t square over sine theta, right? So this sine theta we can write our h. If this is h and this is length L, so we can write h over L. 2x t square h over L. So if this sine theta replaced by h over L, then L go upstairs, right? Upper side 2xl and h t square. So this h stay and t, like you can see t in the like not is dividing. So we can write g equal to 2xl h t square, right? So this we can write about the inclined surface. So you can plug the formula if you like, if you're calculating something from there, you can extract what you need. So next we are going to discuss about our third topics, projectile motion. So projectile motion means we are going to like 2D motion. So 2D motion, one scenario we discussed today about the projectile motion, because in our daily life we saw lots of example of projectile motion. When you see a like baseball playing or any basketball playing, anyone is playing basketball, baseball, or we are throwing something, or in battlefield when there is a cannon, you can see everywhere is projectile motion in action. So what happened to projectile motion? Projectile motion, we have two types of it's a sort of 2D motion, right? Projectile motion. So projectile motion is 2D motion. So we have to draw two lines. One is for vertical lines and another one is horizontal line, right? So another line we draw horizontal line. We can draw horizontal line. So we have two types of line, horizontal line and vertical line. So now we are going to discuss about the projectile motion. So this is y-axis and this is x-axis, horizontal direction, and this is vertical direction. Now, if we throw an object like this direction, we can throw various angle. We can use various angle. But whatever angle we use, whenever we throw an object, and is it going for all the way? Is it going all the way to the space? No. Why? Because our G is working. G is always pulling towards the ground. So when G is working, that means if we throw an object, eventually it will fall, unless we throw more than escape velocity. If we throw or like accelerate an object more than escape velocity, then it will not come back to the ground. But in baseball or basketball, people does not use that much of force. So a baseball player is throwing a baseball, suppose, or a cannon, and a cannon fire a cannonball. You can see it goes straight, is going up, up, up. In some portion, it's going curving, it's curving, and suddenly it's like slowly it's falling, it's stop somewhere, right? So why does this scenario happen? So what is happening here? We will try to understand. So we can see it's going some distance and coming to the ground again. So what happened? From the beginning, the G is working. Each point G is working. Each point G is working downward, right? So it's downward. It's not perpendicular line. It's exactly downward. Our G is working. G is working. So what does that mean? If you are driving a car, suppose you stop, you pressing the brake, what will happen? If you slowly pressing the brake, not like suddenly press, if you're slowly, in constantly you're pressing brake, what will happen? The car will slow down, and car will stop. Same thing happen when we throw with some velocity, it's going. But you can see, if you remember our velocity versus time plot, if the velocity is going like this, that means velocity is decreasing, right? So initially, suppose we have 20 meter per second velocity, right? But it will, every point it will decrease. Why? Because if you remember our formula, our our formula del x, if you remember, del x equal to v initial t plus half at square. If you remember this formula, here acceleration, But in our case, we will not have acceleration. We will have deceleration. Why? Because g is always working opposite direction, right? So in projectile motion, we are going to discuss this stuff. So like I'm not going to discuss the whole theory, because like whole theory it will take a long time, and the video will become very long. So what I'm going to discuss, two scenario. Okay, in one scenario, object is like someone is standing in a building, or some cannon is firing from a building and throwing downward. So we'll have some equations. We have to use those equations to understand more well. So when we have our this scenario, in this scenario, our del y is not equal to 0. Means we have some vertical height. But if is throwing from there, there is no vertical height, right? That means our del y is 0. So if we have a del y, if we have some del y, suppose one person is throwing an object from a like 6-meter height or something. If the object is falling into the ground with some distance, it covers, suppose it's 7-meter distance, the height is 7-meter. How far, how slow it will reach to the ground? You can have different types of question. So if they're asking for the time of flight, we need to use the formula square root of -2 del y over g. We have to use this formula. Why? In this case, our g will be negative. And the value of g will be -9.8. So it will be -9.8. So eventually minus and minus it will cancel out. So our whole formula will be 2 del y by 9.8. See, if someone is throwing a object from 7-meter height, how long it will take to reach the ground? You need to just plug 7-meter here. And if you calculate, you will get some value, right? So if someone is throwing from upper height, it will take more time, right? Because this value is increasing. But it does not matter how much speed we are giving. So it's like that you and your friend staying in some building, in same floor you are staying, you both throw the ball. So if you throw the ball slowly and your friend throw the ball with some speed, but it not gonna change. Is not gonna change because the falling will be together, because you can see there is no velocity is working, right? So now we are going to discuss the time of flight from here. If we throw a object from ground, we are not standing on a roof or anywhere. In that case, what will be our formula? In that case, our formula will be t equal to 2 v naught sine theta g. See, here the speed will make a factor. That means if you are throwing an object from ground, suppose you and your friend is throwing, suppose you give more speed than your friend, that means your one will have more time in the air. That's happened like. So time of flight will be this formula, and this v is initial velocity, what we are giving, and theta is the angle, what we are using. This is the time of flight. And if we are asked to calculate the height, like maximum height, how far it goes, what is the formula for that? Formula for that is v naught square sine square theta over 2g. This is the formula for maximum height, or vertical distance, maximum vertical distance covered by the object. If we ask to calculate how far it goes, or horizontal range, what will be that? Horizontal range we denote by r. So we represent by r, horizontal distance we represent by r. So let me clear this. So what will be your horizontal distance? horizontal distance is this r. From here to here, you can see horizontal distance is r. So r will be v naught square sine 2 theta over g. See, there is some change. So when we calculating height, v naught square sine square theta means if we have sine 45 degree, we have to do sine 45 then whole square. But in this case 2 theta. In this case v naught square is the same sine 2 into 45. 2 into 45 means 90 degree. Okay. So when you are calculating this range, we are using v naught square sine 2 theta over g. But when you are using height, we are using v naught square sine theta square over 2g, not g, 2g. So these are the factor you have to use, but only time, regarding the time, you have to be careful, because if you're throwing from here, your time will be 2 v naught sine theta over g. If you are throwing from some height, your time will be square root of 2 del y over g. If you consider g as a minus 9.8, then you have to use minus sign. If you consider g as a positive, then you need to use minus sign. Basically, you will get some value, not the imaginary number. There is no scope to get imaginary number. So next topics we are going to discuss force. Number four topic we are going to discuss force. So in previous lecture, I already discussed about the force. If we have a force this, what will be the component of x direction? We already know it's f x, that will be f cosine theta, f cosine. Okay. So let me delete this. So it will be f cosine theta, right? And what will be the our vertical component is fy. It will be f sine theta. So these are important factor. Now we are going to use like for the force. What we need to know? We know force equal to ma. Then how we define our acceleration? We can divide by m both side. So our acceleration will be force over mass, right? That is our acceleration. So that is you need to remember this formula. This one we get from Newton's second law of motion. So now we are going to discuss about the vector. When you are discussing about the force, that means it has some direction. So we'll discuss about vector. So if we have a vector A, suppose vector A, how do we represent vector? We represent vector with some axis, right? The component. If it is, we are using two dimension, then ax I hat plus ay j hat. So x means x component. So if we have some like this, two dimension, if we think about two dimension, x and y, so this unit vector for this x direction will be I hat, and unit vector in this direction will be j hat. So if we are representing a vector, suppose we are representing one line. So here we are representing one line like this. So suppose 1, 2, 3, 3, and this one is 1, 2. So 2, 3. So how do we represent this vector? We represent this vector. So 1, 2, 3 x-axis, right? So 3 I hat plus, see this towards 2 j hat. So how do we imagine? We imagine something starting from there, 1, 2, 3 division this direction, and 2 up like this. See, 1, 2. Or we can imagine it's going 2 up and going 3 this division. So both way we are going starting from here, going there, right? Now, if we have a vector A here, and we have a vector B here. So how do I add them? So if it is like this, we can just add them. We can just add them A to B. So what we can do, how can we add our two vector? So if we have a one vector A and another vector B, so how do we add? We add from a starting position to end position. So we state for this. This will be our summation C. So C vector will be summation A plus B. Now you already know A equal to AX I hat plus AY j hat, and B equal to BX I hat plus BY j hat, right? So if we are adding this, that means we will add this X and add this Y, right? Then it's like AX plus BX I hat because and AY plus BY j hat. Why? Because if we have a 2 apple, 3 orange, and your friend has 4 apple, 6 orange, so how many apple will be there? Like how many fruits will be there? You can say 2 plus 4, 6 apple, and 3 plus 6, 9 orange. Like you cannot add apple with orange, or you cannot add orange with apple. So that means you have to use X component with X, Y equal to X, Y. So now we will see one example. Now we'll see one example. Like carefully watch this example, because it's important to understand the vector, like understand the vector clearly. Suppose our A equal to 2I hat plus 3J hat. So that means we straightforward. We will go 1, 2, this, and 3 up. 1, 2, 3. So 1, 2 this way, 2, and 3 up. So our vector will be there. So this will be our vector A, right? This will be our vector. So we are not drawing our path, so we are removing this, because we are not drawing the path how the vector reach there. Okay, but vector can reach there by this or this. So this is a vector A. Now if we vector B equal to suppose 3I and 4J, suppose. So 3I means 1, 2, 3. 3 more I and 4. 1, 2, 3, 4. So maybe it's there. So we are adding, not there. So we are adding them like this. Okay. So maybe I use this quantity as a 8. So it will be easier. 8 means it will be easier to for your eyes to understand the difference. So 8 plus 2, 10. So 2, 3, 4, 5, 6, 7, 8, 9, 10. And 4 is the same. So you can see 4 over 10 somewhere there, right? So we have to draw a line like this. This is our vector B. See, this is our vector B, and this is our vector A. So what is the resultant vector? Resultant vector will be C. So how to reach there C? We have to go 10 division there and 7. So how do we get C? C equal to 8 plus 2, 10I plus 3 plus 4, 7J hat. That's how we do our vector addition. Now you can one of the other important topics is like how to change from X to angle or like force. So if we have a force F, suppose this is 10 Newton, suppose, and if we have an angle like this, angle is suppose 30 degree. So we are asked to find what is the vertical component, or what is the like horizontal component. How do I find that? How do we find that? So we have to use our component, right? Component. So let's start with the so cosine 30 degree. we have to find the cosine 30 and sine 30. Okay. So what is the horizontal component? Fx equal to f sine theta, right? So f is 10 Newton and sine 30 degree. What is 30 degree? Half. Sine 10 Newton into sine 30 degree means half. So 5 Newton. Clear? Then what will be our y? F cosine theta. 10 Newton cosine 30 degree, right? Cosine 30 degree equal to root 3 over 2. So 5 root 3 n. Now, if we know our two component, so here is important topics. So if we have x, y, we need to find r. So from r we can find x, y. How? Y equal to r sine theta, right? X equal to r cosine theta. So we can find y. But what happened if we have x and y? Suppose our component is given. Suppose our component is given, this is 5 and this is 5 root 3. How do I find this 10? It's simple. What you need to do, you have to use Pythagoras theorem. So what is the Pythagoras theorem? R square equal to x square plus y square, right? So let's check. So if we have this x value of this fx equal to 5 Newton, right? So 5 square plus what is our this value? 5 square 5 root into root 3 square. Root 3 square means 3, right? So what we get? 25 plus 25 plus 3 into 3, 75, right? Equal to 100. This 100 equal to 10 square. See? 10 square. And this is 5 root 3 square. This is 5 square. So now, if we know this value, suppose this is our 1. So we use the common like 3 and 4, suppose. So what will be the R? What will be the force? So we can use the Pythagoras theorem, R square equal to x square, y square. So if we can use the Pythagoras theorem, R square, x square plus y square. Now we square root both sides. This square root square cancel out. We left with this, right? So in this case, what will happen? Our x equal to 3 square, y equal to 4 square. So it will be 9 plus 16, square root of 25 means 5. How do I find angle now? Simple. Angle means opposite over adjacent equal to our tan theta or tangent, tan theta equal to y over x. Now, if we are asked to find theta, it will be tan inverse, or you can say arctan y over x. So what is y over x? Tan inverse y means 4 over 3. Now, if you find this, you will find your angle. Okay. So now, in our previous case, if you remember, we had our y equal to 5 root 3 and our x equal to 5. In this case, 5 cancel out. We left with tan inverse root 3. So if you find this root 3 value, you will, the root 3 will be, tan inverse root 3 will be like tan inverse. In our case, our y, if this, then it will be 60 degree. If this is 1 over root 3, if this is root 3 and this is 5, then what we will get? We will get 1 over root 3. 1 over root 3 means 30 degree. So just you need to remember, plug the angle. So how now we understand how we are going to use if we have some force given, theta given. If we ask to find what is the component, we just do f cosine theta, f sine theta. if we have like the component given, fx given, fy given, if we are asked to find f, then it's simple. Fx square plus fy square equal to f, square root of this equal to f, and theta equal to arctan, theta equal to arctan or tan inverse fy over fx. Clear? Because tan theta equal to hypotenuse, like opposite by adjacent. So it should be clear now. So and another thing is important for the force topics, that we know our like attraction due to gravity, we denoted by G, but we have another force, gravitational force. That gravitational force means in our universe every object is attracting each other. Means sun, earth, or me and that like the bottle in the table, or pen in the table, and pen and the bottle is attracting each other. So there is some force. So if we have a object M1, another object M2, if we have, there is an attraction force going on, we can tell it's a gravitational force, and the formula will be G M1 M2 over D square. So what is D here? D is the distance between two objects, right? So, and this value, you know, is constant, 6.67 into 10 to the power minus 11 Newton meter square kilogram square. Now, if we have a object like some value, suppose we have a object like 10 to the power 24, some object mass, and another planet, suppose another planet is like 10 to the power 30 mass, 30 kilograms, suppose, and distance is suppose 8.9 into 10 to the power 12 meter, suppose a kilometer or meter or mile in. So what will be the force? You just need to plug the value of G and you have to multiply M1, M2 and D. Remember, this is the force between these two objects, means what it is attracting this object, same attraction will have for M2. So the value, the force for both will be the same. Because if suppose this is 5 kilogram object and this is 1 kilogram object, it does not means that for 1 kilogram it will be lower, or so it will be similar. So this is the force of gravity. Force like gravitational force, force due to gravity is equal to F equal to mg, where g is our like acceleration. So this g is only for our earth, and if we ask to g for sun, moon, sun, that will be different. So now we are going to discuss about our topics 5, work energy theorem. Topics 5, work energy theorem. So work energy theorem, one thing is important, like the most important thing, conservation of energy. Conservation of energy means energy is, you cannot change, like you cannot destroy or you cannot create any energy. You can change its form, but you cannot produce or you cannot destroy any energy. Suppose I'm talking, I'm using sound wave. How I'm creating this sound? By using my mouth, right? So I'm using my energy to produce the sound. But here we are going to discuss about two types of energy. One is kinetic energy and another one is potential energy. So when we discuss about potential energy, kinetic energy, we can draw a common picture. So the picture is like, if you see, this is a ground, and in ground a box is sitting there in the ground, and the box has a mass m. Okay, the box mass. So what is the potential energy here? So when we talk about potential energy, The formula for potential energy is equal to mgh. That means if we take one box and take it like lift it from the ground and put it somewhere upward, some position up in the ground, then it stores some energy. That is called potential energy. So suppose this height is our h, then our potential energy in this point will be m times g times h. So that means if we are taking it more high, that we will have more potential energy. Why? To take this box from, suppose, one floor to third floor. If you want to take this box from one floor to third floor, you have to use energy. Why you have to use energy? Because gravity is always pulling. Gravity, like due to gravity, due to, due to gravity, we always feel the downward pull, right? So that is our potential energy. So in this case, we can draw some segment to discuss this scenario. We can draw 5 segment. This is position 1, position 1. This is position 2. This is position 3. This is position 4. This is position 5. Okay. So in position 1, what is our potential energy? In position 1. In position 1, our potential energy in position 1. In position 1, what is our potential energy? 0. Why? Because there is no height. So 0. Because the height equal to 0 here. That's why position 1 is 0. So now we are not discussing kinetic energy from the below. When we will come from upward, we will start, because kinetic energy will start working when we have some speed. Okay. So in position 2, what happened? We go some distance, we'll have some energy, potential energy. Okay. So we'll have some potential energy, mgh. It's not h. So suppose we make a scale. Scale means suppose this is 30 joule energy here, potential energy. Okay. Here it's 0 joule because no energy. Now in this position, maybe we can tell it's 25 joule, right? And this position we can say 15 joule. And this position we can say 10 joule. You can see 10 joule. So this is 1, 2, 3, 4, 5, right? So 5 position. So when we take this to some distance, 10 joule, that means when we are going up, our potential energy is increasing. So when we go on top, means number 0.5, what is our potential energy? mgh, and that is 30 joule, means maximum energy. So when potential energy is high, potential energy is high when we go maximum distance. So when we are coming back, our potential energy will decrease. So see, when we take an object 0 to 30 joule, we are working. Like suppose I am using my hand to lift it up. That means I am using this 30 joule. Now, if I release it from the third floor to ground, what will happen? Will I get the energy back to my hand? No. So we are not getting back the energy to my hand. So what will happen to energy? So when we release it, it will start moving. When it start moving, we will start getting kinetic energy. So what is kinetic energy? The formula is half m v square. Simple. Half times mass times velocity. That means if velocity is high, velocity is increasing, kinetic energy also increase. So when we take this box to the top floor, we did not release. Before release, what is the kinetic energy in the position 5? This is, what is the kinetic energy in position 5? 0 joule. Why? Because it's not moving. When we start, when we drop it, so when it start moving, this will start increasing. So in this 0.4, what will be the kinetic energy? 5 joule. Why? Because one thing I already mentioned, the conservation of energy. Energy cannot create or destroy it. So if this 30 joule becomes 25 joule, we are losing 5 joule. This 5 joule converting into kinetic energy. So in this position, what is kinetic energy? 15 joule. And what is potential energy? 15 joule. 10 joule potential energy. What is kinetic energy in this position then? Number 4 position, 2 position. Kinetic energy equal to 30 minus 10, right? 20 joule. So in this, when is just about to touch the ground, potential energy will be 0, or potential energy minimum, our kinetic energy will be maximum, and the amount of energy will be 30 joule. So see, in top our kinetic energy is 0 because it's not moving. When we release it, it's start increasing. Why increasing? Because G is working. What is G? It's acceleration. In each second, the velocity is increasing 9.8 meter per second. So in each second, so unit meter per second square. So in each second, the velocity is increasing. Velocity is increasing means kinetic energy is increasing. This one I'm not this like I saw draw a scenario, but you can also draw a scenario by using your G and other data. So what you need to remember, we need to remember potential energy equal to mgh and kinetic energy equal to half mv square. And we know another term, work done. How much work done? Work done, or another term, del W. W, or what is work done? Work done in change in kinetic energy. If you remember, when we talk about when we release this from here to there, so how much energy was? It was 30 joule. How do we determine? This is the kinetic energy initial, and this is the kinetic energy final. So what is our kinetic energy final? 30 joule. What is our kinetic energy initial? 0 joule. So what is the work done? Change in kinetic energy, 30 joule minus 0 joule. But we need to use formula, right? So change in kinetic energy is work done. So half m v final square minus half m v initial square. See, these are the, so one object is moving 20 meter per second. So now it is moving 60 meter per second. How much work done on the object? Simply, if the object is 5 kilograms, so half into 5 into 60 square minus half into 5 into 20 square. Okay. So this is work done. And few things you need to know for the spring constant. What is the potential energy for the spring? Spring. What is the potential energy spring? It's half k x square. Okay. X is distance and our k is equal to a spring constant. And we know for the force for the spring constant equal to minus kx. And also we know if we have a spring suspended from there with some mass m, if we release it, what will happen? It will go down, back and forth. That means the force working downward due to gravity equal to mg, and it's making a balance. So mg will be kx. Why? Because we know Fs plus Fg equal to our net force. And F is equal to minus Kx and Fg equal to mg, right? And net force is 0. So mg, if we change the side, Kx. So this formula is important for some problem, because if we have our spring constant given, our mass given, what is the distance x? So x we can see mg over k. If our suppose our asked to calculate spring constant, mass given, distance displacement given, x given. So what will be this? It will be mg over x. So we need to use different form of this formula. Now this in potential and kinetic energy is also important for our pendulum. So if we draw a simple pendulum, if we draw some like some positions from here, suppose this is 1 and this is 2, 3, 4, 5. 5 point I'm drawing. Okay. So when we start releasing this point, so what happened? You can see we have some height, right? We have some height from the we have assume there is some height, right? So if we have a height, what is the potential energy in the point 1? So point 1, our potential energy is maximum. Okay. In point 2, it's decreasing. In point 3, we don't have any height, right? So in point 3 or center position, potential energy is equal to 0 or minimum. See, in this point. So in this point, it's start moving. So it's gaining speed. So in this point, our kinetic energy will be maximum. Why? Because we know our total mechanical energy. Mechanical energy. What is the mechanical energy definition? Total mechanical energy. It's kinetic energy, potential energy plus kinetic energy. See, if our kinetic potential energy is maximum here, then we will not have any room for kinetic energy. Means it's not moving, so it's 0. So potential energy max and 0 is kinetic energy in position 1. So now if I draw clearly, like it's not, the line should be like this with the some string length. Okay. So in this position, like it should, I'm using drawing pad, so maybe my drawing will be not great. So in this position, our potential energy maximum and our kinetic energy minimum or 0 in position A1. In 2, we have some value for both. In 3, our potential energy minimum or 0, but our kinetic energy is maximum, and the value will be half m v square. Okay. In this position, both have value. In this position, again, it's repeat. Potential energy maximum. Because see, speed increasing, then going up, and then g is pulling down. So decreasing, and it's become 0. Again going opposite direction. It's increase, then again decrease, 0. So that's why it's swing forever. It's swing forever. If it's an ideal pendulum, then it will swing forever. So in this position 5, the potential energy will be maximum, but kinetic energy will be 0. So we need to use some more formula here. Like if some value given, suppose if we know potential energy equal to mgh, and that is converting into our kinetic energy half m v square. So in that case, if we find some height given, mass given, if they're asking to find the velocity, how fast the object is moving, so in some point both are equal, right? So if both are equal, then we can write mgh equal to m half m v square, because you remember we had, when we had 30 joule, in some point both were 15 joule, right? Both are 15 joule in some point, right? So in this case, mass cancel out, or v equal to v square equal to if we multiply 2 both side, 2 to cancel out, 2gh, and our v equal to square root of 2gh. Why? Because we take square root both side, so this cancel out. So in pendulum, what happen if this height is given 3 meter? So what's the speed? What is the kinetic energy if someone is asking? So kinetic energy will be half m. So we need the value of m here. Suppose 2 kilogram. 2 kilogram. Usually Bob is not 2 kilogram. It should be a less amount. Suppose 2 kilogram. Then it will be half m 2 kilogram square 2 kilogram into our v. What is v? V will be 2 into 9.8 into 3. Square root of this value. If you plug the value here, you can calculate the v. If you calculate v, you can plug here. Okay. So that's how you can find. Also, in some scenario, our for the pendulum, if we draw clearly for our pendulum, if this is our L and this pendulum is going with some theta angle, we can see we can write our H. What is our H then? What is our H? So you know this string is the same, right? This string same. So whole distance will be L, right? So this whole distance will be L. So we can find this distance, right? We can find this distance. So this is L, right? This is L. So if we projection this, means if we want to find this is horizontal component, right? Means adjacent. So we can write L, this distance, suppose X. So our X we can write L cosine theta, right? So what is this distance? H. H equal to L minus L cosine theta, right? So L we could take common 1 minus cosine theta. So if the length of the wire is given, if we are asked to calculate our height, we can use this formula if the angle is given. Okay, because if I draw more clearly, if you can see, if we have it like, just imagine this is our pendulum's ball. It's going like this, swing like this, swing. I just flip the picture and you can imagine this, right? This is our X theta and this is L. So this also L. Why? Because we are using same string. It's just going like this, right? So this is our L. So whole distance will be L, right? So what is this distance? L minus X, right? And what is our X? L cosine theta. That's how we we can find 1 cosine theta, 1 minus cosine theta. Okay. And one more thing, for total mechanical energy is like potential energy plus kinetic energy, or kinetic energy plus potential energy, both are same. If there is some thermal energy or another form of energy, that means like some loss, we can use some loss. If we have, suppose we are using friction surface, so there is a frictional loss. So whatever loss it is, it will be there. So if we don't get this to equal to total thermal and mechanical energy, that means there is some system loss we can use. But if it's a perfect system, then there are no system loss. Only kinetic energy and potential energy will be equal to the potential energy. So number 6, conservation of energy. Number 6, conservation of energy discussion is almost the same discussion we discuss in the conservation, like work energy theorem. Basically, one work energy theorem, I discuss conservation of energy also. Now, so I'm going to start topic 7, which is conservation of linear momentum. Again, we are using topic 7, So conservation of linear momentum. So when we use the terms conservation, that means it's going to conserve. So first we're going to start is momentum. What is momentum? Momentum means mass times velocity. It's a vector quantity. Definitely. Why? Because velocity is a vector quantity. So conservation of momentum means P total momentum. So momentum before collision. Before collision, total momentum, total before collision. Before collision, before collision, and the momentum after collision. If both are equal, then you can say conservation of linear momentum. So in this case, we can have two scenarios. One is elastic collision. Elastic collision. Yes, elastic collision. And another one is inelastic collision. Okay. So inelastic collision. So elastic collision, our both momentum and kinetic energy both conserved. But in case of our inelastic collision, only momentum conserved. Momentum conserved. Okay. So what does that mean? That means before collision momentum and after collision momentum is same for both case. But before collision kinetic energy and after collision kinetic energy is before collision, after collision is equal only for elastic collision. Clear? So what does that mean? That means if we have some 30 joule kinetic energy before collision, after collision the kinetic energy become suppose 25 joule. Is it elastic or inelastic collision? It's an inelastic collision because kinetic energy is not same. But if before collision 30 joule, after collision 30 joule, then it's a elastic collision, right? And momentum, the unit of momentum, mv, that means kilogram meter per second, right? So momentum, suppose 20 kilogram meter per second. So after collision, it will be 20 kilogram meter per second, whether it's elastic or inelastic collision. Okay. So kinetic energy is not conserved in the inelastic system. Kinetic energy is not conserved. So we can we know if we have an object M1, a billiard ball, or we can see suppose we imagine it's a car, it's moving, and or another billiard ball here M2. So is some have some velocity v1 and it has some velocity suppose v2. So maybe we hit this one very hard and this one is moving slowly. So after some time, suppose M1 and M2 collide. So what will happen? So this is an inelastic collision. So we will write M1 V1 plus M2 V2. And after a collision, if it is going together, then we can write M1 M2 over into V. So this is the after collision, before collision, after collision. Is same. If car is stopping in the signal, a lorry or truck comes and hit the car with some speed V, and after they start going together. So for this we can use this formula. Like we can have some so if the car is stopping, this V will be 0, right? So suppose that lorry is 300 1000 kilogram, suppose lorry, and moving with 5 meter per second speed, suppose. Then 1000 plus 5 is 5000 kilogram meter per second, right? And the truck, suppose the car is 100 kilogram, suppose. but there is no speed, so 0. So what will be this? 5,100. 5,000 plus 100, right? And what is the V? So we can easily calculate this. How? If we see our both sides should be the same, right? So both sides should be the same. So here 100 into 0, 0. 1,000 into 5 equal to 5,000. So here we need to find the M1. M1 1,000 plus 100, not 5,100. V. So you can see what we in this side is 5,000 and this side 1100 V. So what is V? 5,000 divided by 1100. How we get 1100? 1,000 plus 100. M1 1,000 plus 100. This is 1100. So what is V then? V will be 5,000. 5,000 divided by 1100. That will be our V. That's how we do the calculation. So next topics we are going to discuss is centripetal force and linear momentum. Important topics, conservation of linear momentum. Important things is that in elastic collision, both kinetic energy and potential energy is conserved, but in inelastic collision, momentum conserved only. Okay. Now we are going to discuss topics 8, which is centripetal force. Centripetal force. Centripetal force. So in centripetal force, we have formula Fc equal to m v square over r, and we know this is our tangential speed, and tangential speed we can write in terms of our angular speed. So omega r. So then we can write Fc equal to m omega r square r. Then r square and r cancel out. Then omega square r. We can write like this. And we know our tangential is equal to v2 pi r over t. So you might be like t, or you can write this t. So you might be curious how I am writing these equations. No, I am not doing anything magical. Just remember, if we have starting, like when we discuss about the centripetal force, that means one object is moving towards the center, and inside there is a center and moving in circle, right? So in circle it's moving. So in circle it's moving. That means you can see whole distance is covering is 2 pi, right? And what is the perimeter? You know, the perimeter 2 pi r, right? So if the r is bigger, suppose, then our distance will be bigger, right? So this is the distance, and this is the period. Period means starting from here, it's for a whole rotation, how much time required. That is called period. Period, right? That is called our period. Or in it's a sort of time, that's why second. And this is our meter, right? Meter means the radius is meter, but in case this is our angular rotation, so radian. So you can say radian meter per second. That is our tangential speed. So here r equal to radius. Okay. So if our radius is bigger, we will have big value for v. So v equal to tangential speed, which is 2 pi r over t. And what is our omega? Omega is the angular velocity. Like velocity, angular velocity. Angular velocity equal to what we know? 2 pi over t. Because it's a tangential speed. Tangential speed, and this is a angular velocity. So see, tangential speed means like in you can see if the radius is bigger, our tangential speed will be bigger. But angular speed does not depends on the radius. So that's why it's 2 pi over t. So you can see 1 r time is extra. So this 2 pi over t, we can write omega r. That's how we know v equal to omega r. And we know formula Fc equal to centripetal force m v square over r. And we also know Fc equal to m omega square r. How I get to this point? You just plug this omega value. You can see previous page. And what we know about another force? Force equal to ma, right? Ma. So from here, if some asking for what is the acceleration, so centripetal acceleration, we can write mac. Then we can write ac equal to v square over r. That is centripetal acceleration, because m cancel out. Or if we want to use this term as a centripetal acceleration, omega square r. So that is about centripetal force. Now we'll be discussing our next topics, which is harmonic motion. So harmonic motion, we have a spring constant, a spring force, which is k del y, or we can, if you remember, if it is suspended from this position, that's why we are using y term. But if you remember earlier, we can write also kx or k del x, means change in distance, right? So if we have this type of system, like this type of horizontal, then we use this kx term. So basically, fs equal to minus k spring constant, which is opposing. So if you push it, if you push this side, spring wants to go this side. If you pull this side, spring wants to go equilibrium position. That means that's why always negative sign. It's trying to oppose you. That's why it's negative sign. And k del y. And we know this from earlier lecture, Fg equal to mg. If we have suspended spring like this, if we have one spring like from the top, we put some mass and release it, it will have some motion, and it will harmonic motion. Why? Because G is starting to pull this downward, and when it's go down, then spring suddenly understand, oh no, you are doing using opposite force, so spring pull upward. So when it go down, spring start pulling upward and then go up, then again G pull. So it's like that. When in this position, when it's going up, the G is increasing, right? Why G is more having more effect? Because if we are going upward, our potential energy increase. That means G always wants to pull more. So that's why G start dominating here and G pull downward, and here G become smaller because height is smaller. So spring started dominating. So what we know from our previous lectures, mg equal to kx, or we know k del y. So in this case, k is our spring constant, right? So that means k equal to k del mg over del y. If we have f, so if we have our f s equal to fg, right? Fs, like we know, it's not like this. It's like Fs plus Fg is our net force F, and we know Fs equal to k del y, and this is mg, and this is zero net force working on this. So we write k del y equal to mg. We just change the side, and this ky become positive, and we flip it. So what will be our k? K then mg over del y. Or if we ask to find del y, mg over k, you can use any of this formula. And one more thing important for this harmonic motion, the period you can find by using this formula, 2 pi over square root m over k, where m is equal to mass and k is equal to spring constant, right? So we can find also our k. We can find k by using this formula if you have a period given. How? we just square both sides. 2 pi square. And if we square these terms, this square and square root cancel out, m over k. Now we change the position. Like if we put this t here and take this k this side. So what will we get? K equal to 2 pi, 2 into 2, 4 pi square. 4 pi square m over t square. That is the another formula to find the spring constant. Clear? So this is the topics for harmonic motion. And remember, for harmonic motion, you need to understand this we called this Fs equal to minus k del y. This is called Hooke's law. Okay, this is called Hooke's law. Now we are going to discuss our next topics, vibrating string. So topics 10, vibrating string. Here we know V equal to F lambda. This is true for all waves. So if we have a wave, we know what frequency is. Frequency is F equal to 1 over T. Like in a second, how many times it's oscillating? That is called frequency or period. So you can see this whole duration will be our wavelength. Wavelength means whole duration from start one point to another. This is lambda. And frequency, you know, if we have a object like this, if we start from this is frequency. Or other words, frequency is like in 1 second, suppose this. In 1 second, this direction goes. So how many times is going? 1, 2, 3. Suppose how many times is oscillating in 1 second? That is frequency. So if we want to find our velocity, like speed of the wave, this is frequency times lambda, wavelength. Or we can say lambda over t, lambda over period for wavelength. Okay. So this formula is important. So if in this case, in any case, our wavelength is given, frequency is given, what is the spring? We can just use this formula, V equal to F lambda. Suppose our frequency is given, 30 hertz or hertz, or this unit means per second. So 1 over second. So if 30 hertz and lambda is suppose 20 meter, what is the velocity? 30 into 20, 600 meter per second. Clear? And in our vibrating spring, we have a formula F. F is equal to tension in the spring, and is mu lambda square F square. This is the formula for vibrating string. How? Our V square equal to F over mu, because mu is the linear density, mass per length. So we know V equal to F lambda. So F square lambda square equal to F over mu. So we multiply mu both sides. That's why we we know lambda square F square equal to mu. So now if the linear density given, wavelength given, frequency given, you can easily find the tension on the wire. Okay. And always try to remember lambda is the wavelength. But in any case, if our segment is given, suppose if you remember, if we use some segment for standing wave, suppose we use this segment. So this segment L. So what is the value of this L? So you see, this is the 1 lambda, half lambda, 1 lambda, 1.5 lambda. Suppose up to this. What is this? 1 lambda, 2 half lambda, 3 half lambda. So 3 half lambda. Okay. Now if we take this segment, then it will be L equal to lambda only, 1 lambda. If we use only this segment L, then it will be half lambda. So it depends on the number of segment. So we are using. Now we are going to discuss our next and last topics is Boyle's law. 11, Boyle's law. In Boyle's law, we know the pressure is proportional to 1 over volume. So what does that mean? if we have a jar and there is some of like gas or some atoms, so if we increase pressure, if we decrease volume, then pressure will increase. If we decrease volume, pressure will increase. If we increase the volume, pressure will decrease. And this we can write a constant term over 1 over V, volume. Okay. Now we can write PV equal to constant. We can write. And that means if we have different P1, V1, P2, V2, we can write P3, V3 like this. So what does that mean? Suppose a object has pressure 10 kilopascal, suppose kilopascal, and volume suppose 2 liter volume. If we increase the volume 4 liter, what about the pressure? So we know 10 into 2 equal to 20, right? So if 1 become 4, then this will become 5 kilopascal into 4 liter equal to 20. See? So if increased by double, it will reduce half. That means at the end of the day, at the end of the system, both quantity, the multiplication of both quantity should be similar. So here this constant, we represent this constant as nRT. So we represent this, right? So n here, n is number of moles. And R equal to our like R has some value, like it's a constant, and this value is 8.314 when you use joule per Kelvin mole. And when you use atom per like liter, we use 0.82. Okay. So we can use this, and T is equal to temperature. And in our system, when we are like discussing about Boyle's law, we don't change the temperature. It's the unit of temperature will be Kelvin, because you can see here R equal to joule per Kelvin. So what does that mean? N equal to some number of mole, right? Number of mole. And R equal to joule per Kelvin mole, right? And temperature equal to Kelvin. So Kelvin cancel out, mole cancel out. We left with some joule, means some number of joule, means some number of like quantity of value, some constant value we'll left with. So these are the important topics you need to understand, and you need to practice those topics if you want to like familiar with the lab, with the general physics topics discussion. Okay, thank you for paying attention. We are stopping here.